FTIR stands for Fourier transform. Infrared. Have you heard of Fourier transforms?
No, I don't think so.
Okay. They're like our favorite complicated math situation. And when you get into the math, yes, they are complicated and very useful, but also they take quite a bit of like technical knowledge and mathematics. Really, really basically, a Fourier transform is taking a complex signal. So it's just like complicated input and turning it into its components. The best example that I've been given in like a real world application is drinking a smoothie and having a tongue that is sensitive enough to be able to tell there was mango and turmeric and pineapple and like half a banana in there.
Okay.
So there are those foodies as well where you like give them a plate and they're like, oh yes, I can taste every ingredient that you used in there. And often it will be like how much of each as well.
Gotcha.
So we're, mathematically, we're going to take a smoothie and identify its components.
Okay.
FTIR is not used on smoothies. It is used actually on complex waveforms. So if we've got, let's say, we've got like radio waves coming across the air, and we've got a wide range of different wavelengths coming through the air. My detector is going to get some combination of all of these, and I'm not going to attempt it, but you can say I have a high point here, and a high point here, and a high point here. So I probably have a really high point right there.
Mm-hmm.
And here I have a low point, and it's kind of offset from a low point, but it's still kind of high over here. So it'd be like a little lower. All of these signals together. Oh, and that looks also like a wave, I'm realizing. That wasn't the intent there. All of these together is going to make something that maybe looks like this. A more complicated looking wave. And like, if you watch it long enough, there is going to be some repeat. So I've sort of drawn these like 3, 1, 2, 3, and there's like 1, 2, 3, and 1, 2, 3. That one's kind of hidden, but that's because I'm doing it by hand. So you've got this sort of repeat pattern because these wavelengths do repeat over and over and over again, but it's not as simple as just like a sine wave.
Right.
We've got a lot more complexity. And a Fourier transform takes this and turns it backwards into its components.
Gotcha.
Mathematically complicated. I think, like, mentally, not all that complicated. You're like, oh yeah, that is a mess. And it is an addition of a whole bunch of other non-messy things. And we really prefer to work with non-messy things. So we prefer that.
Yes.
So really basically that's what a Fourier transform is. We're not going to do math.
Okay.
Let's talk then about the color spectrum, or the spectrum of electromagnetic rays. Somewhere in the middle is what we call visible light. Do you know the wavelengths of visible light?
200 to 800, something like that.
Very close, 400 to 800. Do you know the unit on those?
Nanometers?
Yeah, nanometers. and we're talking wavelength here, not frequency or energy.
Okay.
A lot of times they will use frequency or energy on these kinds of scales. I'm going to talk about wavelength because that is how FTIR runs. And in this case, I have higher wavelength on the right-hand side, which means I have larger frequency on the left-hand side. And larger frequency is the same as a larger energy or higher energy. It is not relevant to today, but do you know what is smaller wavelength or higher energy than visible light?
No.
What do we get sunburns from?
The sun.
The sun, specifically the UV light coming off of the sun. And we get sunburned because it's a little bit higher energy, which means it's a little bit more dangerous to our bodies. Lower than that, we also have X-rays. We're, pretty scared of X-rays. Those definitely cause damage to us. And then we have gamma rays, and we're very scared of those. Those absolutely cause a lot of damage very quickly. So you can see higher and higher energy on the left-hand side, scarier to the human.
Yes.
On the right-hand side, the next step higher than visible light is going to be infrared. Infrared, and that's kind of what we care about today, is split into 3 sections. We have near IR, we have mid IR, and we have far IR. I know, very surprising. Kind of expansion of those. Near IR is going to be 800 to about 2,500 nanometers. Mid is from 2,500 to 25,000. And then far IR goes up to about 1 million. So you can see these are obviously not like linear designations. We're taking very large steps. Tens of thousands here and then hundreds of thousands here. FTIR is specifically in the mid IR region. This is our FTIR region. I'm gonna not write that because I don't want to write in yellow. That sounds terrible. Above that, we get microwaves, radio waves, we get Wi-Fi, we get 5G, which everyone's scared of, but we've been living with radio waves forever, and so far I think we're fine. Anyway, all of those things are going to be much larger than IR.
Okay.
So we are working in the mid IR kind of range here. And the reason we're doing that is because the energy in the mid IR range lines up really nicely with the energy that it takes to wiggle a covalent bond. Not break. We are not breaking bonds in FTIR. So let's draw. Have you taken organic chemistry?
Taking it right now.
Oh, rock on. So you are familiar then with this notation?
Yes.
Okay. So what I have is I've got 2 hydrogens that are in the screen, like they're on the plane of the screen. I have 1 hydrogen sticking out of the screen, so that's going like straight towards you. And then I've got a hydrogen that's poking into the screen, and it should actually be directly behind the first hydrogen. Like if we were looking at this dead on, it would actually look like this. I have one hydrogen here, and then behind I've got a second hydrogen that's like directly on top of each other.
Right.
We don't draw it that way because it's really hard to see what we're doing when we're doing it that way. But people will often draw those very close to each other to kind of indicate that forward and backwardness of it. But also that doesn't look as pretty, so sometimes people will just make it in a plus.
Yeah.
Oh well. And this carbon and hydrogen bond has a dipole. A dipole is a mismatch in charge. Hydrogen very much prefers to not have electrons. And so what we do is we draw this little, I'm pretty sure it's a delta, but it's the lowercase, not the triangle version of the delta. And we put a little positive next to it. And that's true of all of our hydrogens. They all are this little positive dipole. They are more positive, which because they are kind of pushing their electrons off, it means the carbon is going to be a little bit more negative. It's going to grab the electrons a little more. Another bond is oxygen with literally anything. Oxygen loves electrons. So it pulls electrons towards it. It always is going to be a little bit more negative. And so everything around it tends to be positive.
Right.
So in this case, carbon is slightly dipole negative. But if that carbon were next to an oxygen, the carbon would be dipole positive. So really all it means is that they aren't sharing equally. One is pulling a little harder on that electron than the other. And this is perfect for FTIR. So I have a polar covalent bond here. Polar meaning that some dipole does exist. Covalent, that's going to be specifically like not ionic, not metallic, which means this typically is going to work best for polymers or organic materials because they're the ones that have the lion's share of covalent bonds as far as everything is concerned.
Right.
But there are still plenty of like metals and coatings and things that do also have covalent bonds, so it's not exclusive to organics.
Okay.
And this polar covalent bond typically is going to have a bond strength greater than 435 electron volts. Oops, I don't know why I wrote a W instead of a V. Oh, sorry, 495. Oops. What's fun about this is if we look back at our range of infrared, we're going to go back to our green. 2,500 nanometers is the same as 495 electron volts. 25,000 nanometers is about 49 electron volts, which is a lower energy. So here, when I am talking bond strength, I'm saying it would take usually more than 495 electron volts to break any of these bonds, whatever that is. Mm-hmm. Often, that's not going to be in the visible range, that's going to be in the UV range. That's why like plastics break down in the sunshine, is because I am physically breaking bonds with my UV light.
Mm-hmm. That makes sense.
So their bond strength is going to be something larger than larger energy than this 495, which is convenient because that is the start of the mid-infrared. And we are going to a lower energy as we go closer to the far infrared, with 25,000 being the start of far infrared.
Okay.
That all track so far?
Yeah.
Cool. So when I apply these energies that are lower than the breaking energy of these bonds, but are equivalent to, there's like a thing on the screen, because they're not going to break it, what actually happens is instead I get bending and I get twisting. So I can get these hydrogens twisting around the center carbon. These bonds also can stretch back and forth, kind of like get longer and shorter. Or instead of twisting, they can push apart from each other or toward each other. So what we basically have is sort of slinky-like movement where they're twisting, they're bending, they're kind of like rocking back and forth. There are lots of really good like animations of this process, if I can get it to pull up. Slowly. So here's animated version. I have symmetric stretching and anti-symmetric stretching as my first two, top left and top middle. And you can see this is the same motion where my bond is elongating, but two atoms next to each other are either doing it together on the left side or against each other in the middle. Then I have rocking and wagging, which is the top right and the bottom left. These again are the same, let's see. Sorry, nope, the way they've drawn it, rocking and scissoring. This is again the same motion. So this is them moving kind of in line with the carbon. They're just getting closer and farther apart in scissoring. And then rocking, they're moving together, but they're getting closer and farther apart with the bottom hydrogens. And then wagging and twisting, this kind of bottom left and bottom middle, is rotation. And it's hard to tell in this orientation, but you can see like the wagging is at the back and now it's at the front. And you can tell because the bond sort of like comes around the front of the atom. So a little complicated to tell in this animation, but this is sort of an in and out of screen, that wagging and twisting. And then that's either together with the wagging or against each other with the twisting. So I'm not going to attempt to draw those. This picture here with the arrows is the best I'm gonna do. But we essentially have three modes, and then each of these three modes has a sub-mode where they're either doing it together or against each other. 3 times 2, we've got 6 modes of movement that can happen here. And each of these modes of movement has its own specific energy. Did I write any down? I did not. That's a bummer. I probably should have. Oh no, I did. Before I talk about what energies exactly those are applied to, I'm going to talk a little bit about the graph, because instead of wavelength, or instead of energy, or instead of frequency, we actually have our x-axis in terms of wave number.
What's the difference?
Wave number is 1 over the wavelength. So it's just the inverse of the wavelength. We measure it in inverse centimeters. If you remember from up here, we've got a larger wavelength is the same as a smaller frequency and energy. So these are inversely related, these two. So by flipping the wavelength upside down, I create this inverted relationship. So now I have a higher wave number is equal to a higher frequency, which is the same as a higher energy. They're not exactly the same number as each other, but they are more relational, if that makes sense. So a higher wave number is the same as a higher frequency and a higher energy, where before we had a higher wavelength was inversely, so lower frequency and a lower energy. So this one is inverse relationship. This one is a nice, convenient, kind of direct relationship. And my wave number, I get 400 to 4,000. That is these numbers right here. This is 400 inverse centimeters, and this is 4,000 inverse centimeters. So just unit conversions. Fairly simple, but we are never going to talk about wavelength or energy when we're looking at FTIR. We're going to be talking about these wave number values. And coming back over to my graph, we have studied this extensively. So we actually have these really nice clean tables of data where you can be like, oh, I know exactly how a carbon-hydrogen single bond is going to bend. I know exactly the energy that it takes to bend that bond. So 1450 inverse centimeters is a carbon-hydrogen bend versus 1350 inverse centimeter is a carbon-hydrogen rock. So I've got these two different modes. I've got a bend and we've got a rock, and they're happening at slightly different energies. It takes a little bit more energy to bend a bond than it does to rotate the bond. And that's with that rock, which I think makes logical sense. Bending a material versus like pushing a material. Imagine I've got like a stick. I can push the stick pretty easily, but bending the stick is going to take a little bit more energy, a little more effort. So that's what we're doing here. And my y-axis on my graph is either going to be absorbance or percent transmittance. I will show you both. So absorbance being A, I'm going to usually get something like this. We'll talk about the regions and what all of that means in a second. I'm actually going to copy that. Yeah, we'll get that too. We'll talk about the different regions on here, but what this is telling me is that I have some absorbance here, and a lot of absorbance in this region. And each of these peaks is going to tell me information about what bonds are present in my material. Specifically, what polar covalent bonds are present in the material. We usually will use Raman as a supplementary technique to FTIR. That's a whole separate technique, but Raman is good at non-polar bonds, where FTIR is good at polar bonds. So this is not going to see every single bond, but it is going to give us a good idea of these polar covalent bonds. If I were to draw the percent transmittance versus wave number, it would look the same, but it would be opposite. So instead of having my baseline along the bottom, where I had essentially 0 for my baseline and I was moving upward from that, instead here my baseline is at 100% and my transmission is moving downward from that. So here I can see I've got some absorption because I'm lowering my transmission at those regions. Question? No. Okay. So 0 is down here. Up here is 100% transmission. So 100% transmission means none of my light is being absorbed. It's all being transmitted. And so I assume nothing is being absorbed, meaning 100% is being transmitted. And then I can get this sort of like bumpy signal coming downward. It's the exact same thing. Unfortunately, I've learned that I do not have rotational capabilities on this note-taking software. I wish I did, because if I did, I could grab this.
It doesn't work.
No, I can't. I hate that I can't rotate it. But I could grab this and I would turn it upside down, just like do a full, like 180. And I would end up with this. So absorbance and transmittance are just upside downs of one another. I just cannot show that visually on this particular note-taking software, which is the worst. It's fine. We're fine. Everything's fine. So let's talk a little bit about the regions. We typically break this up into 4 regions. The most notable region, how big is that? That is not big enough. Large, please. The most notable region being on the kind of 400 end of the wavelength of the wave number graph. We call this the fingerprint region.
Is it all the single bonds?
It's going to be a lot of single bonds. Yep, absolutely. A lot of carbon hydrogen stuff. And the reason we call it the fingerprint region is because it is really hard to get any individual peak in there and identify it properly. Let me grab really quickly from the internet the exact wavelength of that so I'm not giving lies. I need AI to leave me all the way alone. Not found. Awesome. Picture does not exist.
Is it 1,200?
It's like 1,400-ish. Of course, none of these things have any sort of actual axis on them. There we go. That's a good looking one. Yeah, 1,400 or 1,500-ish. So we're going from about 400 to about like 1,500. I have drawn this way bigger than it should be on a linear scale. Remembering that we're going to 4,000, just pretend like this is a non-linear scale and we'll be fine. I am going to move this a little bit more center though, because there are more things to draw about. On the right-hand side of the graph, I'm going to get some single bonding stuff. So let's grab, I don't know, blue. So this is going to be other single bonds. Oops, I thought I had clicked. There we go. Most commonly, you're going to see a lot of oxygen-hydrogen. OH bonds are the one that I drew, this kind of this like wide, sorry?
With halogens?
Halogens, yes, halogens can be found in there because they often will have a single bond. That OH is the wide peak. Almost every other peak that you're going to see is going to be a sharper peak, where OH is like a really distinguishable wide peak. You're also going to get carbon hydrogen stretch. Then I've got the triple bond region. I don't know why I didn't go down to the axis on the blue one. That's just, here we are. This is the triple bonds. Nitrogen is a really common thing that's going to triple bond. And then a third color. I haven't done a green. And then I've got double bonds here. Just to put some numbers to it, the single bond region is from 4,000 to about 2,500. Shouldn't have put a comma there, should put a dash. Triple bonds are from about 2,500 to 2,000. And double bonds happen from that 2,000 to that 1,500. So we're definitely not any semblance of like linear here. Come on, there we go. I'm going to redraw that blue because it's going to bother me if I have all of them down to the axis and not the blue. There we go. So generally, this is how we can break it down. If we're expecting to have triple bonds in my material, I would expect to have peaks in this region. Double bonds, I would expect to have peaks in this region. And then I'm always gonna have a little bit of something in that fingerprint region. And we could, in any of these three regions, the single, triple, and double bond regions, I can get individual items. So I can identify an oxygen hydrogen. I can identify a triple bonded nitrogen. In the fingerprint region, we don't attempt any of that sort of picking peak by peak. We really use this similar to a fingerprint where we overlay a known material with this region and we're like, does it match? Does it not match? So this is more comparative. While the other three regions we're going to use a little bit more for identification. Any questions? Good. Line up with your chemistry stuff you've done?
Yeah, organic chemistry.
Okay. Let's talk a little bit about how the instrument works, because I think it's interesting, and so we're going to talk about it. And I'm going to use red because infrared, and so red is just the color. Oh, wait, actually, no. I'm going to use purple because I split the color in a second. So the source of our FTIR, we have actually two sources. We have a laser, and lasers are specifically known for putting out one wavelength. Usually we are using a red laser for FTIR, and that's going to be 632 nanometers. We're also going to have something called a full spectrum IR source. Full spectrum means that it is putting out all of the wavelengths all of the time. And as this, like all of this light comes through, my detector sees every single wavelength at the same time, which means it's getting, if I come back all the way up to the top, something kind of like this very complicated signal here. So the detector is going to get some, nonsense mess here, and it has to separate them out. This is where the Fourier transform part comes in. It's going to separate them out into which wavelengths are present. At 100% transmission, so that would be no sample. I can get something called an interferogram. Which is basically what the detector is seeing. This is all the wavelengths all together. Sorry, I've labeled it as if the x-axis is interferogram. The title of this graph is interferogram. This whole thing we call the interferogram of the FTIR. And it's this very funky looking signal where I've got kind of a straight through line here, and then I get this really like increasingly big zigzaggy situation in the middle. Now, so we'll come back to the exact naming of this interferogram here in a second, because interfere is like things are interfering with one another. So we'll talk about that. It is tricky for the detector to collect every single IR wavelength at the exact same time. Some of them are going to be stronger than others. The wavelength or the source might put out a higher intensity of one wavelength versus another. Some wavelengths might get absorbed a little bit by like the mirrors that are moving the light around. And I need the detector to know what wavelengths are and are not present at 100%, so that when we look at the sample and we see, oh, now I'm missing these couple of wavelengths, it can actually identify that those wavelengths are missing. So what we're gonna do is we have, going back to purple. So from our source, we have our beam of light. Yeah, okay. And I have something in the path of the source light called a beam splitter. The beam splitter is typically made out of potassium bromide, or KBr. And if you've ever looked at like a two-way mirror, or like a really thin layer of like a film on a piece of glass, where you can kind of see through, but you can also kind of see a reflection, that is what a beam splitter does. So beam splitter allows some of the light to go through and reflects some of the light instead. I then stick another mirror in each of those two newly created beam paths. And my red light is going to be again reflected down. When it hits that beam splitter, some of it's going to go through, some of it is going to bounce back. And same thing for the blue. When it bounces off of that mirror in its path, some is going to bounce down and some is going to pass through. I'm going to scooch that over. Oh no. The T's run away. This then recombines and goes into the sample. And then the detector. Now, I've drawn all of these as straight lines, right? But we know for a fact that light, instead of just like being a straight line of nothingness, light has some wavelength. And this is a full IR source, which means I have a little bit of this wavelength, and I have a, oops, my hand got stuck. And I have a little bit of this wavelength, and I have a little bit of this wavelength. So I have, in my purple single line that I've drawn in this illustration, I have every mid-infrared wavelength. All at the same time. Just like how when we're looking at like the world around us, the sun has every visible wavelength plus some other ones, which allows us to see, you know, greens and purples and blues and all the different colors. Those are all different wavelengths. And when light hits something, so I'm going to zoom in just a little bit. When light hits something, like a beam splitter, it's going to maintain its position in the wiggle. That is super non-scientific. Meaning, as it passes through, like, we're not going to have the wavelength, the pattern affected. And this reflection, do you see how this one is starting at its low point here? The reflection is also going to start at its low point. So we started at the low point here, oops. Does that make sense? If this travels, I'll do this. So I have low, high, low, high, low. Let's see, this one travels the same distance. Low, high, low, high, low. These two have now traveled the same distance. Good so far? Because there is more. If we place that secondary mirror at the same distance from one another, then the bounce back again, we're going to start at the low, and the bounce back is actually going to follow. Let's see, I'm going to change my purple color ever so slightly so it's a little more obvious. But it's going to follow exactly back on itself. So when it hits this mirror, it's in a low position, and it's going to travel exactly back on the same path that it traveled. Meaning now on the backwards path, they're both starting on low. And we end up with the exact same, so we have two of this wave, and they are sitting right on top of each other. Really hard to draw because this is all time related, and my picture is just static. I can't just like show time. So as long as the distance between these two is the same, I'm gonna end up with the exact same pattern back. Now let's say I extend the distance on just one of these mirrors. I make this one a little bit longer. Are these two waves gonna come back and be exactly in sync with each other? No. They might actually come out of sync to the point where they cancel one another out. So I'm actually going to redraw this just a little bit. So let's say instead my mirror is a little farther. That means that this wavelength completes a little bit more. And when they come back together, I'll actually just pull because I drew it already. They may come back and look something a little bit more like this. Where now instead of being in line, they are perfectly out of line.
They need to be parallel to each other?
Everything on this is parallel because the mirrors are aligned. What I'm talking about here is the highs and the lows of the wave may or may not be aligned. So what I'm talking about here is that in these ones, if I set these on top of each other, I end up with a wave that kind of looks like this. That's effectively my wave coming out instead of this right here. This upper example right here is going to cause constructive interference, which means the detector is going to get a strong signal. Because these two waves add together and we're getting two of the exact same wave, it appears as though this is one really strong wave. In this case, though, I get destructive interference. The detector gets weak or no signal. What all of this means.
What does it look like here?
Oh, sorry, it's the same thing, so I just didn't draw that extra reflection because like it wouldn't have to, but like these would also cancel out that direction, or in this direction they would also be in line with each other. Real hastily drawn. I just didn't draw those because this is a messy enough diagram to try to explain anyway. We call this thing the interferometer. What we're doing is we're creating interference. That's this guy or this guy. We're creating interference. This mirror has the ability, it's on a little motor. It moves back and forth. This mirror is stationary. So we can create this distance as part of the design. And the goal is that at some distances, some wavelengths are going to be destructive, but others will be constructive. And then maybe here, this one's destructive, but that one's constructive. So by moving this back and forth, different wavelengths are going to come through versus others.
How many mirrors you can use?
How many what?
Mirrors you can use.
Mirrors. We use 2 mirrors and an interferogram. There are additional mirrors outside of all of this to direct the light to where we want it to be. But the interferogram, we just have 2 directions. The light can either pass through the beam splitter or bounce off the beam splitter. So we have a mirror in each of those 2 directions. So the interferogram is what is creating, the interferometer is what's creating the interferogram. That is the signal that we are getting through to the detector as this mirror is like back and forth.
Is that always moving?
When you're not using the instrument, it probably doesn't keep moving, but every time you're collecting data, it is moving, yes.
Like there's no baseline, it's just there.
No, because if we had a baseline, if it was holding still, we would have either this situation or this situation, where some wavelengths would just always be destructive and some wavelengths would always be constructive. We'd be missing a portion of our data. So what happens is we can create like a table. I'm gonna move back to my original pinkish purple. Position and wavelengths. And I can create this table. At position 1, I get this wavelength, yes wavelength, no wavelength, yes wavelength, no wavelength, no wavelength, yes, yes, yes. And this would be like the detector is seeing, it is seeing these wavelengths and it's not seeing these wavelengths. At position 2, so that would be maybe it moves a little bit to the right-hand side, we're going to start missing some of the wavelengths. And at position 3, this is a really like wide range, but the detector is like, I collect data about this wavelength at this position. And I collect data about this wavelength at these positions. And I collect data about this wavelength at this position. And so it knows, depending on the position of that mirror on the right-hand side, which wavelengths might be present so that it can more effectively do, all the way back up to the top, this Fourier transform. It knows what wavelengths are possible, and it can kind of subtract out what wavelengths are and are not there. Remembering that when this, twist, bend, whatever is happening, this wavelength and this wavelength are being absorbed. So the sample is going to take these away, and the detector will not receive those wavelengths. So the detector will know, I should see this wavelength in this position. If that wavelength is absent when I do my Fourier transform, it knows that this has been absorbed by the sample. That makes sense? I think the interferometer is a really cool bit of technology that is like fairly simple as far as like the math of it goes, where we've got the wavelength and we've got the distance between mirrors. The biggest trick in an interferometer is knowing the exact position of this mirror.
Why?
Because we are working on the range of, say, like 3,000 nanometers. That's 3 micrometers. The next wavelength bigger than that is 3,001 nanometers. I have a difference of 0.001 microns. Having a motor that is this sensitive is tricky. So instead of trying to figure out a motor that is sensitive to the nanometer, we use a laser. Laser. So I told you we'd come back to that. We use the laser to identify the mirror's exact position within nanometers. Because I have one specific wavelength coming out of the laser, I know exactly what to expect as far as which position is going to show which wavelength. I essentially have one column of like, this position is going to give me this signal for that one wavelength. This position is going to give me this signal for that one wavelength. So the laser does the same thing where it goes in and back out, and then it goes in and back out. And so we have the laser signal coming through here as well. And all the laser is doing is helping us know the mirror's exact position. So we had two paths here. We could either get a motor with sensitivity of nanometers. That's expensive, and that is high tech. And it's really sensitive to vibration. This is an expensive and easy to break system. The other option is laser. Well, the other option, instead of having a motor that just knows where it is to measure position. This is less expensive. It's relatively low tech because we're already doing all the math anyway. It's just one more wavelength. And it's only sensitive to the laser alignment, which can be done once and then pretty much left alone. So this is absolutely sort of our gold standard here. There is no point in doing something that is expensive and harder to do. We choose cheaper and easier pretty much always.
It's almost the same results.
It is better results because the sensitivity on this was sensitive to vibration. You're gonna get really crappy data if your motor like comes off just a little bit. Your detector's not gonna have any idea what wavelengths it's looking at. So we have in this situation two detectors.
Hey, how are you?
Good.
One detector for running the Fourier transform on the infrared light, and one for measuring the laser for motor position. There's one other little like consideration on here. Oh, here it is. I mentioned that this beam splitter is made out of KBr. That's potassium bromide. KBr is a salt. And when we push the salt really hard together, it creates this nice little kind of solid thing. And it's kind of see-through and kind of reflective, which makes it a really great beam splitter. The problem is that salt is water soluble. So any humidity or exposure to water is going to dissolve our beam splitter. The beam splitter is so crucial to operations here. KBR is the best beam splitter. It has the least absorbance of those extra wavelengths, so it's not going to interfere with the light really at all. But humidity is its huge downfall. So we have to have a dry FTIR. That can be done either with a desiccant. A desiccant is a particle. Oops, I am drawing that completely backwards. It's a particle that has really fine porosity. These are little like pores here. And because the pores are so small, water gets drawn into them. So just like it absorbs water out of the air. It's a drying material. We also will often purge with dry gas. Now, whether that's air, like dry air, just someone has pre-dried the oxygen and nitrogen, or it could be just straight nitrogen. But either way, we're flowing this sort of like dry gas over it. Questions up to this point? Well, that's unfortunate. Questions? No? Okay. Applications. You can run almost anything on an FTIR. Most common, we're going to be looking at solids or powders that are plastic. That's going to be like 90% of the traffic that you see on a general purpose FTIR is going to be plastics and polymers. We can absolutely, oh good heavens, that was fun and annoying. We can all absolutely do liquids. That's really great for studying like drug concentrations. We can also do gases, as long as we have something to contain the gas in the beam. Is it common? Yes and no. So gases you would use as sort of a subset to another technique. So let's say you're doing TGA, which is where you heat up the sample and you try to get gases to come off the sample. That's one application of it. You want to know what gas is coming off of the instrument as it runs. And so you could analyze the gas in real time. So
Does the machine do that for you?
you could buy an instrument that hooks up to an FTIR, or you could just stick the two instruments next to each other and kind of grab some tubing to pull the air off of the TGA and flow it through the FTIR. So you can build it yourself. There are instruments that come pre-installed with that kind of thing. Gases, you also could be looking at stability of materials. So looking at how a material like breaks down in the presence of certain gases. With powders, the old way is a KBR pellet. So KBR, coming back, same material as was up here. But we would mix our powder with KBR and then press it so that it becomes this sort of like solid mass of material. And then I send my IR beam through it. The problem is KBR is water soluble. We're right back to the original problem, which means that any sort of humidity inside of this pellet or surrounding the pellet is going to cause problems. So modern gold standard is an attachment called an ATR crystal.
What does ATR stand for?
We'll get there. You good?
Yeah.
Okay. ATR stands for attenuated total reflection. And what we have for ATR is we have a diamond. And we
Diamond?
Mhm.
Real diamond?
A real live material diamond. Probably lab grown because that's the way to do it. And my light path, sorry, I've been drawing my light as purple this whole time, so we're gonna keep that up. My light comes in and it's refracted off the interior surface. So my beam actually kind of reflects off the inside of my ATR, of my diamond. This diamond. And I've got my detector over here. When it interacts with that surface right there, there's the tiniest little bit of light that escapes. And we're talking like nanometer, maybe micrometer depth, just barely. So if I stick my sample like a liquid or a powder, so let's say I have a powder right here, I stick it on the surface and I press it down to like densify it and make sure it's really like contacting the diamond. I get, and I'm gonna pull this to a tiny little, I get this tiny little interaction right here. The way I've drawn it, my powder is not densified enough, and so my IR beam would hit air rather than powder. So you wanna make sure that you are nice and densified against the surface of the crystal. But then we get this little bit of interaction and we get a little bit of absorbance so that this beam right here is missing just like the tiniest bit of those wavelengths. What's nice about this is it's not sensitive to moisture and it's a lot more repeatable than doing this KBR pellet way. So all of this is best, kind of the current state of things for powders. Yeah. Let's talk just a little bit about what we do with the data. You can do stuff as simple as just like identifying individual peaks, just like what I was showing earlier, where you're like, I have a nitrogen triple bond, I have a carbon hydrogen single bond. That's gonna be everywhere, but you can identify individual peaks, and if that's helpful to you, you can compare one thing to another. So we can do comparative.
We can draw the microstructure after that.
Yes, so we can compare one sample to another to just look at changes. So like before and after heating, how does it change? We can also identify peaks and draw or assume molecular structure. That's what you're gonna do in like an organic chemistry class. They'll hand you a scan and they're like, what material is this? And you have to take all the bonds and kind of fit them together. FTIR in an organic chemistry class, you're often going to see also a Raman spectrum or an NMR spectrum, because FTIR on its own, just having a list of peaks, is not all the information you need to know what is up with the material. So you do have to do that with other techniques like NMR or Raman. You also can do quantitative or identification, work with a database. So you can take your scan, you can compare it to a whole bunch of known materials, and you can use a computer to quantify or identify your material. When we're talking polymers, you can do a degree of polymerization. Look at you. You can look at like consistency. Like between batches, QA, QC kind of thing, quality assurance. That's QA, quality assurance. Why do I keep writing? Wow, my handwriting is terrible on this particular section. QA for quality assurance or QC for quality control.